Hey everybody in Honors Pre-Calculus. Welcome to lesson 1.5, Combinations of Functions. We have 6 lessons in Unit 1, so this is our 5th lesson of 6. In this lesson, you will be able to add, subtract, multiply, divide, and compose functions, which is when you do a function inside of another function. And you will evaluate, write, and graph piecewise functions. The essential question today is how can operations be used to combine functions algebraically and graphically? Now, some of this is going to come naturally to you, but other of the lesson today will be new. So make sure you are keeping track of everything. All right, I'm going to pause and switch over to notes. All right, so here are our notes. 1.5, combinations of functions. We're going to start with sum, difference, product, and quotient, which of course mean add, subtract, multiply, and divide. And the only thing that might be new over here is the fact that if we have two functions that we're adding together, a notation for that, kind of a shortcut way of writing it, is like this. If you have f plus g of x, it translates to f of x plus g of x. That's the same thing. If we have f minus g of x, that's f of x minus g of x. If we have f times g of x, it's f of x times g of x. And like this would mean divide. And of course, when we're dividing, the denominator cannot be 0. We're also going to take a second to look at the domain for a quotient of functions. And the domain is the intersection of the domain of f and g, and the denominator may not equal 0. We'll take a look at what that means when we get to one of the examples. Composition of functions means f of g of x, which can be written like this. If you have a little open circle instead of multiply, it means it's f of g of x, written like this. We'll see some examples of that as well. We've got the idea of a piecewise function here, a function defined by 2 or more equations over a specified domain. For example, something like this. We should be fairly familiar with that from our previous lessons. And today, something brand new is going to be this thing called the difference quotient, which is key in calculus, but we're going to see it and preview it today. So let's take a look at example 1. Arithmetic combinations of functions. So in letter A, if we're given f of x and g of x, we're supposed to find f plus g of x, and then evaluate the sum when x equals 3. So let's write this down. So if we have f plus g of x. That means we're going to take 2x plus 1 and add x squared plus 2x minus 1. So this isn't too bad. We just combine like terms. We have 1 x squared term. We have plus 4x, and plus 1 minus 1 cancels out. So that's the first answer to the question. And then it says evaluate the sum when x equals 3. So if we wanted to write that in the proper notation, it would be f plus g of 3, like that. But we don't have to start over because we already have the simplified version of this expression. So now we're just going to plug in 3 for x. So we'll have 3 squared plus 4 times 3. And so we have 9 plus 12. And that'll be 21. All right, so that's it. So we're just going to do that over and over each time. So for letter B, if we have f of x and g of x, they're actually the same. And now we're finding f minus g of x. So it's going to be 2x plus 1 minus x squared plus 2x minus 1. So we're going to subtract these. Remember, the negative distributes. So we have negative x squared, 2x minus 2x cancels out, and then we have 1 minus negative 1, so 1 plus 1, so we have positive 2. And we're going to do f minus g of 2, because that's what the question asks for. And so instead of going through all these steps again, I'm just going to plug 2 into the answer that we already got. So we'll have negative 2 squared plus 2. So we have negative 4 plus 2, which is negative 2. Very nice, very nice. This is a key moment to point out, and just to remind you, the difference between negative x squared written like that and negative x in parentheses squared. So if the negative's in front and there's no parentheses, when we plug in for x, we assume that it's like this, where the negative is still in front and stays there after you square the number. Don't forget that. So for in this one, the negative stays. And in this one, the negative gets squared, right? That's a good reminder right there. Let's look at letter C. Now we're doing f times g of x. And let's see what we got here. So we're going to plug in x squared times x minus 3. And so we have to distribute the x squared, and we get x cubed minus 3x squared. Okay, so that's the product. And now we're going to evaluate when x equals 4. So we have f times g of 4. We just plug in 4 in for x in what we have. So we have 4 cubed, which is 64, minus 3 times 16, which is going to be 64 minus 3 times 16, which is 48. And 64 minus 48 is 16. All right, last one. This one has several different parts. We're going to do f over g of x and g over f of x, and then we're going to find the domains so we can practice that concept. So let's start with f over g of x. And all we're going to do here is write f of x over g of x and call it a day. So there's our first answer. So sometimes we say that we don't want a denominator to have a square root in it if we're calling it simplified. That is true, but we're just going to leave it like this because there's nothing else that we're doing with that function. We can just leave it, and we'll take a look at the domains. But this question didn't say anything about simplifying, so there's no square root in the denominator. So we're just going to leave it like that. It's much nicer, simpler, and easier to leave it like that. And for g over f of x, we just kind of switch it. So we have the g of x function on top, the f of x function on the bottom. All right, so now let's think about the domain. Remember, the domain is the x values that have y values for each of these functions. So if we go back up to the top, we saw that the domain for a quotient of functions is the intersection of the domains of f and g. That word intersection there just means the overlap. So wherever the domains of f and g overlap, and additionally, the denominator may not equal 0. So I think the first thing we should do down here is figure out where did the domains of f of x and g of x overlap. So we're going to start by just finding the domain of f and the domain of g. So I usually write that by just d of f like this. So the domain of f and square root of x. So the question becomes, what values am I allowed to plug in for x in this function? And you might remember that if we have a negative number and we take the square root, it's an imaginary answer. And we'll talk about imaginary numbers in Unit 2. But for now, we just know that that's not a real answer. So no negative numbers are going to work. So our domain and interval notation is going to be from 0 to infinity. And we include 0 because you can't take the square root of 0. The square root of 0 is 0. So that works. So now we have to take the domain of g. And g is the square root of 4 minus x squared. So the question is, what values can I plug into 4 minus x squared and still be positive so that when I square root, I get a real answer? I could just try using the calculator here. If I plug in square root of 4 minus x squared, you'll see it looks like this. We can go to the table, and it works from -2 to 2. That'll also work if we think about plugging in numbers here. Anything between -2 and 2 will be a value once you square it that's less than or equal to 4. So when I do 4 minus that number, it'll still be positive. Anything that's greater than 2, like think about plugging in 3 for x, now we have 4 minus 9. Okay, so that's a negative number, so it's going to be a square root. The same thing happens if we plug in negative 3. It becomes 4 minus 9, and that's a negative number inside of a square root. So this works from negative 2 to 2. And it includes the negative 2 and the positive 2 for the same reason that we included the 0, because if we plug in 2, you get 4 minus 4 is 0, and we can take the square root of 0. The same thing happens if you plug in negative 2, 4 minus 4 is 0. So that's our domain of f and our domain of g. But the question wanted us to find the domain of f over g and the domain of g over f. Okay, so what we need to do now is think about, where do these overlap? So where do f and g both exist? And if we think about 0 to infinity and we think about negative 2 to 2, they overlap from 0 to 2, right? 0 to 2 are a part of both of those intervals. And 2 is included in both, because 2 is included here, and 2 is between 0 and infinity, so it's definitely included in the first one. And 0 is included here, and 0 is right in the middle here, so it's included in both. So that's our overlap. And so the last step then, if we look back at the top again, is the denominator may not equal 0. So we have to look. In f over g, what value makes this denominator 0? And it would be the 2 or the negative 2, right? 2 squared is 4, negative 2 squared is 4, 4 minus 4 is 0. So we can't have 2 or negative 2. Well, negative 2 is not even in our overlap interval in the first place. 2 is. So when we write our f over g, we can't include the 2. So it goes like that. And our domain of g over f, remember the first step is to think about the overlap of the domains of f and g, which we already found right here. And now we have to make sure the denominator doesn't equal 0. So we look over here, square root of x, 0 is going to cause that denominator to be 0. So when we write our interval this time, we restart with this. We just can't include the 0. And that's our 2 additional answers here. All right, so just to recap, first we just found f over g and g over f. Then we found the domain of f and the domain of g. You can use the calculator to help. You can plug in 0 and see where the boundaries are. This is what we get. We find the overlap of the 2 domains, and then we have to exclude anything that makes a denominator equal to 0. So the first one is bracket 0, comma 2 parentheses. The second one is parentheses 0, comma 2 bracket. All right. Great, that is the end of example 1. Let's keep going. Composition of functions. Example 2, given f of x and g of x, find the following. F of g of x. So for letter A, we start with f of g of x, and I like to rewrite it from this notation to this notation because it makes more sense in my head. And we always want to start on the inside and work our way out. So if we have g of x on the inside, I'm going to plug that in. So instead of g of x, I write 4 minus x squared. And now we want to do f of x, but plug 4 minus x squared in for x. So we're going to end up with 4 minus x squared in replacing the x plus 2. So our final answer is going to be 4 plus 2, which is 6 minus x squared. All right. In letter B, we're going to find g of f of x. Now, if we just switch the order, it doesn't necessarily mean that we're going to get the same answer. So let's test this and see what we get. So first, we start on the inside. We plug in f of x, which is x plus 2. And now we plug x plus 2 in for x in g of x. So we're going to get 4 minus x plus 2 squared, right? See, I took the x and instead of an x, I'm substituting in x plus 2. It's kind of weird because both of these terms have x in them, but that's the way we do it. So instead of 4 minus x squared, it's 4 minus x plus 2 squared. And let's multiply this out and see what happens. So we're going to have 4 minus x squared plus 4x plus 4 once we FOIL. And then I can distribute the negative and combine like terms. We end up with negative x squared minus 4x, and 4 minus 4 cancels out. All right, last one is g of f of negative 2. Now, we just found g of f of x. So all we need to do now is plug in negative 2 into this. But I'm going to show you the long way to do it because sometimes you're not already going to have this work finished. So if we have g of f of negative 2, first thing we do, we always start on the inside with these composition of functions. So we have f of negative 2. So the first thing we're going to do is figure that out. So we plug in negative 2 for x here, and we get negative 2 plus 2. So that's 0. So now we do the outer of 0. And so we go to over here, we have 4 minus 0 squared, and it's going to be 4. All right, so that's the kind of starting from scratch way to do it. If you look right here, we could have also plugged in negative 2 into this expression because that's kind of already solved out for us. Negative 2 squared is 4, so we have negative 4 minus 4 times negative 2. So it's negative 4 plus 8, which gives us that same 4. All right. Next up, example 3, finding the domain of a composite function. So now we're going to practice that same skill, finding f of g of x, but finding the domain of that solution. And it's a little trickier than just finding the domain of a normal function. And so I wrote out the steps here for you to fill in on your own notes. And we don't need this much space. So if you have this printed out, feel free to write this in this exact box on your sheet. So here's what we're going to do. To find the domain of a composition of functions like f of g of x, we first find the domain of g of x, the inside function. Then we find the domain of f of g of x as its own function. So we don't care just about f of x. The g of x has to go through the f of x. So we think about the domain of f of g of x. And then step 3, the domain of our actual f of g of x is the intersection or overlap of those first two intervals. So let's try this. So step 1, find the domain of g of x, because our composition of functions is set up the same way as this. The domain of g is, let's see, so g is this, square root of 9 minus x squared. That looks a lot like the function that we were finding the domain of earlier. It's going to be, if you take a look at the graph, it's another half circle, and it goes from negative 3 to 3. So first we do that. Step 2, find the domain of f of g of x as its own function. So let's just try to find f of g of x, and then we'll see what the domain of it is as of its own function. So f of g of x means we have f of square root of 9 minus x squared, which would be, we plug square root of 9 minus x squared in for x in the f function. So I'm replacing this x with the square root of 9 minus x squared. The squared minus 9 stays there. So the square and the square root cancel out, so we get 9 minus x squared minus 9. And 9 minus 9 is 0, so we get negative x squared. So now the question is, what is the domain of f of g of x as its own function? That's a negative. It looks kind of sideways, but that's negative. So the domain of f of g of x as its own function. And so the question becomes, what numbers can I plug in to x here in negative x squared? Well, you can plug anything in to negative x squared. Nothing's going to be excluded from this. I can plug in 5. I can plug in 5 million. I can plug negative 18 gazillion. And you can always square it and then make it negative. It's not changing anything. So this is actually negative infinity. Whoa, negative infinity to infinity. So now, step 3, we find the intersection or the overlap of the two intervals. Well, this interval is all real numbers. So this is going to create our bounds. So our overlap is -3 to 3. All right, I also wanted to say that I had a teaching assistant who was a high school senior a few years ago who had a pretty cool visual to represent this. So I want you to think about if we had like a flock of birds representing all real numbers that are trying to fly through some barriers. So they're all going this way, okay? And let's say that we have some barrier that's here, and that's our internal function, our g of x, and then maybe the next one goes like this, and that's our f of g of x. So by the time we get to the outer, it's the inner and the outer that we care about. And we're going to see the domain is how many of the birds actually get through all the way to the other side. And that's kind of like thinking about the overlap. So this one gets stuck, this one makes it through the first one and then gets stuck. This one makes it through, this one makes it through, and then these ones down here get stuck. Okay, so it's all about which numbers or birds can make it through all of the barricades. So if the first one was -3 to 3, and the second one was -infinity to infinity, which numbers make it through both? And in this case, the overlap is -3 to 3, including the -3 and the 3 with the brackets. All right. Example 4, piecewise function. Evaluate the function at the requested x values. So first up, we have x equals -1. So if we're doing f of -1, what we do here is we think about that this expression on top is only valid when x is less than 0. This expression at the bottom is only valid when x is greater than or equal to 0. So when x is -1, that's less than 0. We're only looking at the top function. So we plug into x squared plus 1. All right, and so we're going to get 1 plus 1 or 2. For the second question, we're trying to find f of 0. 0 is greater than or equal to 0. So we're going to only use the bottom expression and plug in 0 for x, because that's what we're plugging in. And so we get -1. And then for question C, f of 1. 1 is greater than or equal to 0, so we use the bottom function, plug in 1, so it's 1 minus 1, and we get 0. All right, that's the basics of piecewise functions. Let's keep going. All right, last thing here is the difference quotient. The difference quotient is used in the definition of the derivative, which is fundamental to calculus, right? This class is called pre-calc for a reason, because it's prepping you for calculus. And you don't necessarily need to know why this is important in calculus at this point, but the formula computes the slope of the line through 2 points on the graph of f. These are the points with x coordinates, x, and x plus h. So if you want to think about what this fraction actually is, before we actually try to solve it, think about if we have 2 points and their x values are x and x plus h. We don't know their y values, so we're just going to use function notation to represent their y values. So it's going to be f of x and f of x plus h. So what we can do here is use the slope formula. So the slope is going to be y2 minus y1 over x2 minus x1. And on the bottom here, the x's can cancel out. So we end up with f of x plus h minus f of x over h. And that is the difference quotient. So that's going to be pretty important when you get to calculus. But right now, we're just going to practice how do we actually plug in to that to get a solution. So if f of x equals x squared minus 4x plus 7, we're going to find f of x plus h minus f of x all over h. So I always think the easiest way to start these is to find the more complicated function notation first. So before you even try to plug into that massive fraction, we're just going to find f of x plus h. So remember, this means that we go back to the f of x function, and every time that there was an x, we're substituting x plus h in instead. So we're going to have x plus h squared minus 4 times x plus h plus 7. And so the first thing here we're going to do is FOIL. So we have x squared plus xh plus xh is plus 2xh plus h squared. We can distribute the negative 4, so we get negative 4x, negative 4h, and then plus 7. And unfortunately, we have no like terms, so we're stuck like that. All right, so the next step is going to be to plug in the entire fraction. So if we have f of x plus h minus f of x all over h, what we're going to do here is on top, the first term, f of x plus h, is what we just found. So we have x squared plus 2xh plus h squared minus 4x minus 4h plus 7. And then we subtract the f of x. So f of x is given to us at the very beginning. So we have x squared minus 4x plus 7. And now in our denominator is h. We don't have anything to plug in for h. H is h, so we're just going to leave that as h. So we plugged in for f of x plus h, and we plugged in for f of x. The next step is going to be to start to simplify this. I know it looks a little bit crazy right now, but it'll get better. So I'm going to distribute this negative to here. This becomes positive, this becomes negative. And look what starts to happen here. The x squared term and the negative x squared term cancel each other out. There's a negative 4x and a positive 4x. And there's a positive 7 and a negative 7. So all of those go away, and we're left with 2xh plus h squared minus 4h all over h. Okay, so now we're in a position where all of our terms in our numerator have h in them. And that's what we're dividing by. So we can divide 1h out of each term from the numerator. And we're left with 2x plus h minus 4. So this h cancels out. This one loses its exponent because we divide 1h out. So we lose 1 from the exponent. We're left with 1. And this one loses its h. And that is our final answer. All right, we're going to do the same thing for letter B. I took up some of the space, but we'll have to make it work. So for letter B, first thing I'm going to do is find f of x plus h. And the next thing we're going to do is plug into the difference quotient. So we end up with x squared plus 2xh plus h squared minus x minus h plus 1 minus x squared minus x plus 1, because that's our f of x that we're plugging in here. And that's all over h. So the x squareds cancel, the negative x's cancel, and the 1's cancel because of this minus sign right here. So we're left this time with 2xh plus h squared minus h divided by h. And now we're going to divide h out of each term. So 2xh divided by h is 2x. H squared divided by h is h. And h divided by h is 1. It's very common for students to forget that h divided by h is 1, and not that that just goes away completely. You have to have that minus 1 there. So make sure you have that in your final answer. And there we go. That is the end of the notes. So thank you very much for watching, and let me know if you have any questions.